Welcome everyone to part one of my 3D printed screw compressor project. One of the things I've always found very interesting in automotive world is the use of superchargers and turbochargers to increase horsepower. And where I would love to make a 3D printed turbocharger, it's really not feasible with the speeds that they have to reach. But another, I think just as cool thing is a supercharger. There's a bunch of different types of superchargers out there, but one of the ones that I've been most fascinated with is the actual twin screw supercharger, which uses asymmetric rotors to compress the air and create boost. The mathematics behind these and how they're actually designed is fascinating, and it's not an easy task by any means to actually design these types of rotors. They've got their own design software, they've got their own CFD software. It's really its own little niche as to how these screw compressors work. And so I found it very interesting over the past several months to learn more about these. I'm not going to pretend that my modeling or FDM 3D printing is going to replicate the extremely tight tolerances that these types of compressors use, but my goal really is if I can just make something that's a cool display model and might make some cool noises and, stretch goal of maybe potentially being an over-engineered tire inflator. Someday if I get an SLA printer, I may try this again and see what results I can get with better tolerances. Also of note, in case you're thinking about potentially making a 3D printed supercharger for your small engine from this design, this particular model's rotor profile is not going to be ideal for use in a supercharger application. Also, now AMR makes an AMR 300 and there's an AMR 500, which are small superchargers for engines under 2 liters, and they're less than $250 US, which is an unbelievable deal. So before I launch into actually designing this in CAD, I want to just highlight a couple of different types of superchargers that often get mixed up. Of course, there's the centrifugal supercharger, which operates more like a turbocharger. But the oldest type of supercharger that you would see out there is a root-style blower. And the difference is that a root-style blower has rotors like this, where both rotors are symmetrical. And it's not actually compressing the air along its length like a twin screw compressor would. It's actually compressing the air more like a fan. Actually, it's just a high pressure fan. So the inlet's on this side and the exhaust is being on this side, and they just spin, throw the air out against the housing and force it out. Not unlike you might see in a oil pump in a car. Beauty of this design was it was very easy to manufacture and to design, and didn't require the CNC type mills and things to manufacture. But a much better design that came along is the twin screw supercharger, and that actually compresses air a little bit differently. So the air comes in at one end, is actually thrown out against the housing and forced in between the vanes of the 2 rotors and compressed along the length of the screw and exhausted out the other side. Okay, there's several different things to know about screw compressors. There's a couple of different types based on how they're actually lubricated. There's oil lubricated and there's actually dry screw compressors. Oil lubricated screw compressors, kind of like it sounds, actually use oil for lubrication. They typically inject oil somewhere along the length of the screw compressor, and they use the oil for lubrication between the rotors as well as actually enhancing the sealing between the rotors. And it also, the oil vapor itself is used to cool the air charge as it is being compressed. One of the unique things about oil screw compressors is that they can achieve a much higher pressure ratio. So that's essentially how many times they can actually compress the air. A compressor with the better sealing is able to achieve a pressure ratio of about 13 to 1. So that means if you have 1 psi on this side, you're able to get 13 psi potentially out on the other side, depending on the design. So the other style of screw compressor is, of course, the dry screw compressor. And they use this typically in smaller screw compressors, not industrial units. They might use them, for superchargers or for medical devices where they can't have oil vapor in the air being compressed. The difference between dry screw compressors is typically they actually have a set of timing gears that actually keep the rotors separate from each other, and they actually never touch. So the gears essentially act as a synchronizer between the two rotors, so that there's a very, very, very small gap between the two rotors at any one time. Because a dry compressor does not have the oil to help at sealing, they can really only achieve a compression ratio of about 3 to 1. So that's 1 psi in, they might get 3 psi out. And because there's no oil for cooling, dry compressors typically use a charge cooler of some type to cool the air. To achieve higher pressure ratios with dry screw compressors, there's typically multiple stages that feed into each other with like an intercooler in between. Another cool thing about screw compressors is that the rotors are actually just gears. They can have different ratios of lobes, like 3 to 5 ratio, 4 to 6, 4 to 4. And because they are gears, like for example, these two would be a ratio of 3 to 5, that this one would have to rotate 5 times for every time the female would have to rotate 3. And in this particular case, it's a 4 to 6 ratio. Different numbers of lobes are useful for different purposes. There are lobe arrangements that are ideal for oil or just dry compressors. Some lobe arrangements are better at moving high volumes of air, and some for achieving higher pressure ratios. This particular screw compressor is a kind of a middle-of-the-road 4 to 6 lobe design that can be used in oil or dry with a decent pressure ratio. Also, because these are just forms of gears, of course, you can create a helix. This one here is twisted about 330 degrees over its length, and this is twisted 220 degrees over its length. Now, what's interesting is, unlike a normal spur gear, is that the actual twist angles have to follow the same ratio as the lobes. So for the screw compressor we're building, it's going to be a 4 to 6 ratio with something called a Stasic end profile and a 330 degree main rotor twist angle, and using Stasic's non-patented design. I know that's a mouthful, and I won't go into all the technical details of how every type of screw charger is designed, but all that means is essentially the rotors themselves are asymmetrical to each other, as well as the actual lobes are asymmetrical in design. Go ahead and include a link to a grad paper written by Stasic that covers this in more detail, and the mathematics behind these rotors. I think that's actually one of the most fascinating things, if you're actually a math person, is to go see how they actually develop these rotors. So I think the easiest way to do this is to be able to walk through the design in CAD, starting off with the rotors and kind of working our way out. So to design the rotors themselves, Stasic has some great grad papers on his non-patented designs, as well as some other designs. And what I did is I went into C# and I actually created a program that I've actually lost over the years, but it actually creates an SVG file that can be imported into Fusion 360 and actually turned into a sketch. So once you have the profile, it's pretty straightforward from there. You just actually are doing a sweep with the profile over an axis and putting a twist angle on it. The one thing that I found out from some earlier prototypes was that getting the clearance between these rotors and the housing is very difficult to do in one go. And I ended up printing out multiple copies of these housings, which would take, 50 to 100 meters of filament every time I did that. So the design approach I've taken now is to actually have a liner that the rotors actually come in contact with, and this is inside the housing. So there's not too much unique about the liner other than it's fairly easy to be able to reprint, and it also will allow me to test different materials for the rotors and for the liner itself. The only thing that you have here is on the actual air intake is there's just a little divider that helps with the efficiency of the compressor itself. So next up is the actual outer housing. So this surrounds the rotors themselves. Right here is the intake port. So this is where the air comes into the compressor. And over here is the actual exhaust port. And what actually happens is these rotors actually spin. This one goes this direction, so it'll go clockwise, and this one goes counterclockwise. And it actually throws the air against the outside of the housing. And I don't know if you can see this, but actually as it comes into the port here, it's actually open on the top half of the housing here so that the air can actually wrap around the rotor, and it actually matches the profile that the rotor cuts as it's spinning, so that it can suck the air around about, I'd say that's about 80% or so of the rotor. Now I'm not sure mathematically if that's accurate, but based on pictures I saw, this is roughly what I was seeing in other screw compressors. It's the same way with the actual inlet and the outlet. The inlet is roughly 3 times as big as the in-surface area as the outlet. This is again based on pictures that I saw. I'm not sure what the actual mathematics are behind this. I couldn't find any information on this. It's actually really hard to find information on screw compressor design. It's a very proprietary type information, and the companies that actually manufacture these don't really share their information with the general public too much. So now that we've actually got the housing here, I'll actually bring in, we'll call the actual ends here. So the intake end, we've got some bearings, some O-rings, and the exhaust end. And I'm going to go ahead, I'm actually going to switch back to the design view here so that I can slice this in half and show you the guts of the housing. And actually I'm going to hide the rotors here. So this is what the guts of the housing look like. It's pretty straightforward. What I've done here is actually just have some 608 skateboard bearings on either end. I do have 2 on the exhaust side because these are actually, the rotors themselves are helical gears, so there is some axial load. And in real screw compressors, of course, they use some sort of thrust bearing. I have some O-ring seals on both ends. On this end, it's just a single O-ring seal because this isn't really the high pressure end, the intake end. And on this end, we have double O-ring seals. It's yet to be seen whether or not we actually develop enough pressure to actually need 2 O-rings on there. The other purpose for these is potentially, sometime in the future, I might play with actually filling the ends with oil so that they can have additional lubrication for the bearings. And on this side, I'll actually show you the timing gears. Let's go ahead and show those. So these 2 timing gears have the same ratio as the rotors themselves. And so what I'll do is I'll actually set it up so that there's a minimal amount of play between the rotors, and the gears should actually keep them separated at all times. Now, for a small compressor like this and with fairly lubricative material like plastic, you don't necessarily need these gears, and I may play with not having them in place later. But But for now, I just wanted to do it because it's kind of cool, and we'll see what actually happens in the end. So again, we have just the shafts coming through here. This is a mains-driven compressor, which is a fairly typical design for these compressors. And what that just means is that the male rotor is the one actually with the input. And I'll go ahead and show the rotors again so that you can actually see this is the input rod here. And then I'll show the let's see, intake cover itself. So this will be where the actual power comes from the motors and actually drives the rotors themselves. I'll have a set of pulleys here that I'm still working on the design for, and a couple of motors up here that will actually drive those with a big GT2 timing belt. I think that'll work the best. It'll be kind of belt driven, just like real superchargers in cars are. I also added a, for fun because it's cool, a velocity stack. I'm sure that will probably do almost nothing. Let's see, what else do we have on here? Here at the exhaust end, I do have the ability to adjust the thrust. So essentially I have some caps that can be printed at different tolerances to actually change the preload on the rotors, the bearings themselves, and then those will just screw in with 3 M2 screws into some brass inserts. I used brass inserts on all of this. Now I know there's going to be a lot of people out there worried about this exploding on me, but the reality is, being a dry compressor, and even if I play with injecting some oil, you're never going to, realistically see more than, let's say, 40 to 60 psi if I'm extremely, extremely lucky. This housing is very overbuilt. I did everything with 5 walls on the prints, so you could literally, I can stand on this housing and it doesn't even flex. There's nowhere, even at the thinnest parts between the rotors and the ends and the caps, there's nothing with less than I think 12 walls is the thinnest it gets. So there's very, very little safety concerns I have with this particular design from an explosion type standpoint. And I'll be printing all the housing out of PETG, which again just adds a little bit of extra protection. So this side here is the exhaust. This is designed to actually match the profile of the rotors, as you can see, to maximize the pressure, or to minimize, the pressure loss as it's actually exhausting the gas out. But on top of here, I'll actually have a elbow, essentially, that's just a 90-degree turn that transitions between that strange shape at the outlet of the compressor to a more rounded shape. And then to this, I'll actually put a O-ring in there, and then I'll actually have an air port so that I can thread in some sort of fitting, so that maybe I can stick a pressure gauge on this and see what kind of pressures we're going to get out of it. So right now I'm about halfway through printing all the parts. Everything is being printed in PETG. I did some small scale tests, as you could see, with PLA, and they almost immediately began to melt. So hopefully the PETG will hold up enough to get me through the actual testing of this model. I know that later I'll probably have to reprint the rotors out of Delrin or Nylon 12. But I want to go ahead and just see what kind of performance I can actually get out of this before I go invest in more expensive materials. Realistically, I've got probably another couple days of printing left. I found the slower that I print, the better the accuracy, and honestly, I have over 1 kilogram of PETG just in this housing itself, so it's definitely very strong. Next video, I'm hoping to be able to start fitting all this together and maybe see if we can fire this thing up. Let me know in the comments if you have any good ideas for ways to test this thing's performance. I hope everyone enjoyed this format. I know the trend on YouTube right now is just to skip to the end and show the project working all in one video. But my hope is that walking everyone through the design will help people appreciate more about how these machines actually work. And realistically, I wouldn't be releasing videos very often if I only skip to the end. Anyways, if you like this video, please hit that like button. And if you want to see more content like this, please consider subscribing. Thanks.